The way that GPT-4 works would be functionally identical if the entire field of adversarial machine learning dropped off the face of the earth. Like, nothing that we learned in adversarial machine learning impacted the way that we designed the biggest models today. Like, no one trained them to be adversarially robust. OpenAI and Google changed their APIs. They broke functionality to make their APIs a little bit less functional because of this attack. Because they have viewed the attack as sufficiently advanced that they want to make sure that this can't be done.
All right, everyone. Welcome to another episode of the TWIML AI podcast. I am your host, Sam Charrington. Today, I'm joined by Nicholas Carlini. Nicholas is a research scientist at Google DeepMind. Nicholas joined us early last year to discuss his groundbreaking paper, Extracting Training Data from Large Language Models, and his most recent work in the area, stealing part of a production language model, earned him a Best Paper Award at the 2024 ICML conference. We'll be digging into that paper as well as his other Best Paper winning work focused on large-scale application of differential privacy in machine learning. Before we get going, be sure to take a moment to hit that subscribe button wherever you listen to today's show. Nicholas, welcome back to the podcast.
Yeah, thanks for having me here.
I'm super excited to jump into our conversation. I will refer folks back to our last convo for your full background, but I did notice something in your bio that I hadn't noticed last time, and that is that you like to write interesting coding puzzles like tic-tac-toe games in a single printf call, or Doom clones in JavaScript, or a fully functional CPU on top of Conway's Game of Life. What is that all about?
I feel like programming should be fun. And most people get into computer science because they find joy in writing fun programs. And I wanted people to understand that people can both do serious research and also have a good time with things that have absolutely no practical relevance, but at the same time are just entertaining. And it's a thing that that people should have fun with the things that they're working with. And so yeah, I wanted to call it some of the things that I do that are interesting and fun, but have they shouldn't exist. There's not no one asked for this to happen. It's entertaining.
That's awesome. Awesome. So as I mentioned, the last time we spoke, we were talking about some of your early work in exploring this intersection of security and large language models. Large language models as a field has exploded since that time. Maybe a good way to ease into the conversation about the specific paper is to have you talk a little bit about that explosion from your perspective. Like, how has the landscape evolved since you started studying it?
Yeah. So yeah, in the last year and a half, uh, so the last time we spoke was just after ChatGPT's launch, and so in some sense, very little has changed, because in the field of adversarial machine learning, we're still worried about the exact same problems. We're still worried about attacks that we used to call adversarial examples and people now seem to call prompt injection. Um, we're still worried about poisoning, where someone manipulates the training data set. We're still worried about data stealing, where someone tries to recover data model was trained on. We're worried about the same set of problems, but on the other hand, everything has changed, because it's no longer a field that is focused on problems that may exist in some hypothetical scenario. It's now a question of attacks that someone actually would want to implement because people are using this in real production environments. And so a bunch of our recent work has been trying to think about this problem from this angle of, why would someone who is an attacker actually want to achieve some goal, and not why might a security researcher want to write a paper on some problem that they think might be interesting in the future. And so the problems have been the same, but the applicability of these problems to the real world has gone up by quite a lot.
Mm-hmm. And I inferred from the paper that the this idea of model stealing has become its own kind of standalone field of research.
Yeah, so model stealing as a field has been around for quite some time. In machine learning, the very early paper on this, I mean, early machine learning world, I think, was 2016 by one of the co-authors in this paper, Florian Tramer and his collaborators, where they showed how if someone deploys a simple machine learning model as some prediction service, and I interact with the model, that I can actually steal the model the person has trained by making API queries. And the way that they did this was they focused on some very, very simple classifiers, like a linear classifier that takes the input, does a dot product with a single, linear sort of scalar, and then returns you the output. Some very simple classifiers like this, and they showed that it worked in those settings. And there has since then been a very long field of work that tries to make this more and more practical. Um, and so the way that this tends to go, that this field basically has two directions. There's one line of work focused on trying to steal a model that is roughly as good as you can by making queries. So what this looks like is you have your model and I make queries on like the same data distribution I care about, and then I do some kind of distillation, or I use the fact that your model is good to train my own copy that's like as similar as your model as I can make it. And here what all I care about is getting high accuracy, like on the same data distribution. There's another line of work that tries to do something more like model extraction, where I'm trying
Yeah.
to actually
Get at the
recover,
internals.
yeah, like the exact weights of your model. Like I want a bit for bit copy of what you have on your disk. And it turns out that this is actually impossible. In that there are many different models you could have that represent the same function. You could scale one layer by 2 and the next layer by 1/2, right? And so when you perform your computation, you'll initially have your computation going one way, you'll multiply by 2, then divide by 2 immediately afterwards, and the output will be identical. Like I can't tell, and so I can't actually recover the same bits that you have on disk, but I can recover what's called a functionally equivalent model. That like up to some invariance is as similar as possible that I could hope to achieve. And so in prior work, let's say in 2020, we and another one of the co-authors on the same paper, David Rolnick, wrote independently papers that showed that if you have a neural network with only ReLU activations that only has, let's say, under like 50 neurons, that works in floating point 64 precision, that I can feed in arbitrary inputs, that I get full arbitrary outputs, then it is possible to steal this model in a functionally equivalent way.
Okay.
But no one uses models that have like 50 neurons that work in float 64 and all of these things.
Yeah.
And so after we both wrote this paper at the same time, Florian, the person who originally did model stealing, David, the person who wrote the other paper concurrent, and I got on a call together and we're like, okay, like what can we try and do? How can we extend this work? And we tried to come up with some ideas. And one of the ideas we came up with was actually the idea that eventually became this paper from 6 months ago. Um, but the so we had an idea, but the idea had no practical utility yet. And so we just like we said, okay, fine, like we can't find something to do. Let's sort of like let's wait. Um, and then you ask sort of what at the beginning, like what's changed? Well, the language models became a thing, and it actually now is the case. Like if you think about it, it's now actually a thing in the real world where someone will deploy a model that you care about, that you can make queries to, but you don't actually know what the model is. Right? This is what a language model API is. All of OpenAI and Google and Anthropic and everyone like have these production language models that are do great, but they're not going to tell you exactly what the weights on the models are. They're not going to give it to you. And so we went back and we started thinking about this model stealing problem again, and we came across this idea we had from probably 2020, 2021, and realized like this is now an important problem that we had some ideas on how to make some improvements. So that's roughly how this paper happened.
Now, was the idea problem focused or approach focused?
Yeah, both, right? So we had the approach. So maybe let me tell you what we can do in this paper. In this paper, we show it is possible to recover one layer of a language model. So language models, like any other machine learning model, are a sequence of layers. And what we can do is we can steal the last layer of the model, which turns the internal representation into a sequence of tokens or words or whatever you have. And in many models, the first layer and the last layer are the same, they're shared. And so this also gives you what's called the token embedding matrix, which turns the input tokens into the hidden state. Now, not all models are this way, but many models are. They do share these two layers. And so what we learn is the last one. And if the last one's the same as the first one, we also learn the first one.
And a couple
And
of comments.
yeah, go ahead.
One is to contrast the paper that we talked about last time. Again, this is February 23. This was focused on extracting training data as
Yes.
opposed to the model itself.
Yes.
And I guess I want you to speak a little bit to the relationship between those two and the way you think about them and the approaches and their utility.
Yeah. So they're both about stealing, but they're about stealing entirely different things. So one of them, yeah, is
Although, like, presumably, the way and the reason you're stealing the training data is that it is somehow embedded in the model. So, extracting training data is kind of model stealing
yeah, okay, sure, yes, okay. So from this perspective, yeah. But so maybe let me talk about the motivation. So in security, there's a question of like who is being harmed by an attack. Like when I'm doing an attack, like who am I trying to get at? When I'm doing model stealing, I'm generally harming the person who trained the model. Because like I have spent, whatever, millions of dollars training my very fancy model, and someone else can try and get a copy of it without having spent that much money.
versus training data extraction is more a privacy concern in your.
Exactly. I'm worried that, some hospital is going to train a model on some patient records, and they're going to try and do a good thing for the world and make it so that some small hospital in the middle of nowhere can like feed in their medical scans and get like a reasonable diagnosis when previously they had no specialist on hand. And that would be great if they could do that. But it turns out that given access to the model, I can learn about the people the model was trained on, and so there's concerns of patient privacy. And so I'm not harming the hospital directly because they've actually published their model. I'm harming the patients who participated in this scheme. And so this is the big difference on the motivation here. And then the techniques are also fairly different. So when you're doing data stealing, for the most part, the way that we do this is we try and mimic the kind of data the model may have been trained on, and we try and get it to emit that kind of data at test time. Whereas for the model stealing piece, what we try and do recently is use we treat these things as mathematical objects, and we treat this like a cryptographic problem where like you have this thing that exists and we try and steal it. And this is what we tried to do. So the paper that I mentioned that we published in 2020, we published our paper at Crypto, which is like the conference where people submit new block ciphers and new theoretical encryption algorithms and whatever, these kinds of things. And the reason we put it there is we tried to draw this analogy between model stealing and cryptanalysis of ciphers. And like this is the way that we framed the problem. We framed the problem not as some machine learning thing, but as you have this mathematical object. It happens to be a language model or a vision model or something, but like what it's doing internally is some matrix multiplies with some nonlinearities. Like this is a thing that is just a mathematical object you can study independent of how it was derived. And cryptographers are really good at that kind of thing. And so we tried to frame this as that kind of problem to get some of that community focused and working on this problem.
The second question I had, you were talking about the extracting this final embedding layer, which often correlates to the initial embedding layer. There's a lot of excitement about embeddings. Embeddings are like increasing importance. Does that mean that like extracting that piece in and of itself is outsized has outsized value relative to other parts of the model that you might be able to extract?
Yeah, we don't know. This I think is a good question. So the question of what you would do with it. So we have some things that some applications of what I could do with stealing this part of the model. You can speed up some forms of generating adversarial examples in some ways. You can speed up some other attacks that need the ability to make arbitrary queries to the model. But a big part of what we wanted to try and do was to say, previously, the literature has focused on, let's imagine a hypothetical threat model, and then let's see what is the strongest attack that I can make possible there. And you change the threat model so that your attack becomes really strong. And this is, I said we can steal a full model as long as it had this long list of assumptions that were all false in practice. What we wanted to do is we wanted to say, maybe on occasion we should write papers that look at what is true in the real world and then try and see what is the best that we can achieve in the real world. And obviously, it's not going to be nearly as strong as we can achieve in some hypothetical future where various things were true. But this is the world we're living in now. And so let's look at that world and try and see what the strongest attacks we can do are here, because we know it will have some real world impact. And that was the setup for this paper is maybe this model is maybe this layer is very interesting. Maybe it's not, but it's the best that we can actually do right now. And my hope is that, or maybe my hope isn't, I don't know, depending on which you're viewing this, you could extend this to a second layer, right? Once you've done one, maybe you can do two. Once you've done two, maybe you can do three. And this is how the attacks that we wrote previously worked. Previously, we would go first layer, second layer, third layer, fourth layer, and we'd sort of recover them one by one. This time we're going backwards. We got the last layer. Maybe you can use that and get the second to last layer. Now, our techniques are not going to help you there, but someone else who's smart might be able to come up with a way of doing that. And this is the general question and the way we wanted to try and reframe the field a little bit so that we could get some people looking at some real world problems.
The implication there being that you were very much targeting that last layer as opposed to you had an idea of an attack and, oh, look, it produced the last layer.
So this is where it comes to so we had this idea in mind of let's try and attack real things. And I think I'm even in the last time we talked, I might have mentioned this a little bit, where this is the thing that we've been trying to think about for a while. And in general, the way that I try and find research ideas is I try to first ask, what do we want to achieve? And then ask, what are the things that we can do? And then you just compute the cross product. You look at all of the things that we're able to achieve, we'll look at all of the things that we actually want, and then we try and see which ones match. And so we had this idea in 2021 or so of a way to recover part of a model. And then we had this sort of realization that we want to be able to steal these production language models. And so we already had both these ideas. We just needed to connect them. And that's what happened sometime almost a year ago today. And then we spent some time writing the paper up, and then I got the paper into ICML.
I guess I'm really trying to get at the, I want to steal part of a language model. A production language model is different than I want to steal the embedding projection layer
I
of a
see.
language model. And
Okay,
so
so
was
why
that
that
just
layer?
a low hanging fruit, or was that what appeared as you started attacking? Or did you look at the model as a white box entity and say, I can probably get that thing?
Great. Okay. Maybe to be more clear, stealing the last layer is the thing that we learned how to do in 2021.
Ah, okay.
So the attack idea that we had in 2021 was exactly this, of how to recover the last layer of a model that had certain properties.
Okay.
And no interesting model at the time had those properties.
Mm,
And it was not interesting to recover any part of this model if we could make one up. And then when it turned out that these language models became a thing and we tried to think about stealing, we went to well, what are all the things that we know how to do? And was oh, here's this idea that we came up with in 2021 that was not very useful at the time. And it has to be adapted because at the time we were looking at ReLU networks, and Language models aren't value networks, and so there are some tweaks we had to make, but we had the idea for how to steal the last layer of a model with certain properties at that time, and then it turned out that many of those properties happened to be true, some not, that we had to adapt, some that were, that we could just transfer directly over.
So how does the attack work?
Yeah, okay. So I will hopefully not scare anyone away, but you will need a little bit of linear algebra knowledge here. So let me just try and say this in the simplest possible way. Um, so a language model emits, when you make predictions from it, a probability distribution over a bunch of tokens. So it says, if you have my name is, it will have very high probability on valid names and very low probability on like the word cat. Okay. So many models have, let's say, 100,000 possible tokens that they know. This is roughly like words or something like this. And so you can visualize the space of outputs from a model as 100,000 dimensional space. Now, one thing you could ask is what happens if I query on many different random inputs and plot the outputs of the model in this high dimensional space? One thing you could imagine is maybe I'm drawing points randomly in this 100,000 dimensional space. And that's what people usually think about. It turns out, though, that that's not the case. Actually, despite the fact that these logit vectors live in a 100,000 dimensional space, they actually all lie on a much smaller dimensional subspace. Let's say like maybe 8,000 dimensional subspace. The way you should visualize this is you can have a bunch of points in 3 dimensions and you can have them all put on a plane, a 2-dimensional plane. So you can have a bunch of points in some very high dimensional space, but they all live on some lower dimensional subspace of that. And that's the case for language models. And there's this very particular reason why, which is what language models do is they work in some small hidden space. The hidden space of the language model is the width of the network. And this is, roughly 4,000, 8,000, something like this for various models. And the final thing that the model does is it projects from the hidden space up to the output embedding space with a single linear transformation. And if you remember your linear algebra, you cannot increase the dimensionality of a space by a linear transformation. And so what you do is you take the hidden space and you just linearly scale it up into an 8,000 dimensional subspace of this 100,000 dimensional vector space, which is the outputs that the model produces. Okay. Now this is true, and okay, now I'm going to skip over a bunch of details, except to say first one thing. First, let's observe that this lets you learn the size or the width of a model fairly easily. This is sort of the first warm-up attack that we have. First thing that you can do is you can learn how wide the model is, and the way that you do this is you make many, many, many different queries to the model, and then you just plot them all, and you look, what is the dimensionality of the subspace that all these points lie in? And it will tell you, let's say, 8,000 or something, or 4,000 or something. And now I've learned a single number about the model which was secret. Now this number in itself is also a little bit interesting because the size gives you something which people don't publish, right? No one knows how big GPT-4 or GPT-3.5 or any of the Claude models are. But if you run this attack in this way, you can learn not the exact size, but you can learn the width. Only the height is missing. And the height and width are usually highly correlated, and so I can learn some significant information there. And I think this in and of itself is also interesting because, okay, so for example, we worked with OpenAI to run this attack on their models. We got their permission. Lots of excitement there of asking Google lawyers to ask if I can steal OpenAI's models, at which they tell me no. And then okay. But after we all agreed on this, I ran the attack. And what this means is there are now 2 groups of people in the world who know how wide GPT 3.5 is. There are current and former employees of OpenAI and me.
Mm-hmm.
The way this is an actual thing you would want to learn, and actually the best way to learn it is through this attack, which is something I think is interesting because this is not the case for many other attacks in security, right? Or in adversarial machine learning, where there are like other ways you could achieve the same goal. But like here, like the best way to achieve this is through this attack. And so we have this piece of knowledge.
You talked about querying the model.
Yeah.
What is the nature of these queries? Are they, human readable, a collection of human readable queries, a collection of nonsense that has statistical properties? Like, what are we talking about here?
So it actually doesn't matter. In the language of cryptanalysis, all we need is known plaintexts. I don't need to choose the inputs that I make. I just need to know what they were. So all that I need is a bunch of different inputs. And so in practice, what I did,
So if
because
you had a large user, you could passively observe their queries and responses and perform your attack without actually executing new queries, or at least this initial
okay,
part of it.
with one caveat, which is that I need to know the entire probability vector for a given input. And so most language models don't reveal this to you. They only give you, let's say, the top 5 probabilities. So what I have to do is I do have to make many queries to the model with the same prefix, with the same prompt, and ask the model to reveal to me the probabilities of all of the tokens one after the other. So I can't just do it entirely passively. But which prefixes I choose don't matter.
So
So
you're asking the model, you're presenting a fair degree of repetition so that you can reliably extract the distribution of
yes,
output tokens.
correct. So I'll take the same prefix, whatever the prefix is, and I'll ask the model for the output probabilities, and I will do this, 100 times or 1,000 times, so I can recover the probability distribution over outputs. And there's the majority of the technical work in the paper is exactly in how you do this efficiently, because there are lots of strategies you could take depending on exactly what APIs are made available.
And do you also, presumably, I guess, you also need to, so that's one dimension where you're like crafting your sequences, but then another is like some degree of coverage so that you can broadly scope out the
So that
distribution.
matters less.
Oh, really? Okay.
Yeah. So all we need is to be able to just because models are highly nonlinear, and so as long as you make any arbitrary queries, you'll cover basically the whole space because you pay per
Dig into that a
token.
little bit more. How does the non-linearity translate to covering the whole space? I guess when I hear something's nonlinear and you're trying to extract information about it, my intuition would have been that, well, you need very broad coverage because learning
Yeah, yeah, yeah.
something would be very local.
Okay. Yes. So this is a good distinction. We are recovering the last layer, which is just a linear projection of the hidden state. So what we are learning is just a linear thing. All we need is inputs that, in the dimensionality of the final hidden state, are sparsely distributed around. And because the rest of the model is very nonlinear, we can rely on that to give us points that are essentially randomly sampled from the embedding space. But we're only learning the final linear projection. And that's what makes it easy to do that piece.
Got it. So the linearity of the final layer kind of says that you only need a small number of parameters. Like if you can learn all the points of a line with
Exactly.
your m and your b, and
Yep.
then the internal nonlinearity says that you're going to get a broad sampling on this whatever that space is. You don't need to craft that yourself.
Exactly right. Yeah,
Got
you're
it.
relying on the nonlinearity of the first piece to give you the sampling, and you're relying on the fact that there are not many parameters for the second piece. Now, okay, in a simple world where you're doing a line, yeah, this is like mx plus b. You do this in pre-algebra kind of things. What we're trying to learn is a matrix times some x plus some bias b. And it turns out that the techniques you could do here are essentially the exact same things as the things that you learn in algebra. They're just over some big giant matrix. And it turns out that there's an algorithm for it. It turns out the singular value decomposition gives you this. It's not immediately obvious why, but that's like very in the weeds. It turns out that this is a thing that you can compute, and you can recover it in this way. Um,
So the attack is a matrix inversion.
Essentially, yes. Yeah, what we're trying to do is we're trying to invert some matrix, and yeah, there are reasons why it makes sense to try and do this. And no, it's one of these things where the attack is not hard because of the math. Like, the attack is hard
It's hard
because
because of the scale.
yeah, right, exactly. And so you need to like get all the things working in the right way, and yeah, most of the technical work, as I said, was recovering these probability vectors because no one wants to give you these directly. You have to do some analysis on how to actually recover these things, and yeah, and so that's what makes things a little bit tricky. And then there's a lot of analysis that happens in the paper where we try and formally characterize exactly what's going on here. And this is where it's nice to have theory people as collaborators. I am not a theory person. My knowledge does roughly stop at singular value decomposition, but all of them are able to like tell me, oh, here's this attack that works. I go to them and say like, why does this work? And they can do the analysis and explain like the query complexity and like here's what you should in principle want to be able to do, and then we can go and take that and actually implement it.
That's awesome. And so getting from the collection of query responses or the pair of queries and responses to the matrix that you need to invert, what's involved there? Or is that
I
an
think
obvious
nothing.
thing, or is
No,
that
yeah, so it's not obvious, but the answer is nothing. So
okay?
all once I have so I'm going to form a sequence. I'm going to form a matrix. Here's my matrix looks like. For each row, it is the logit vector for for each token, one after the other. So I sort of look at the token for the first token, second token, third token, fourth token. I place the probabilities or the logits in each of these for a row, and I form the matrix that has many rows. Each row corresponds to a different query. And then this is the matrix that I invert. This is on this matrix I compute the singular value decomposition, and it turns out that this gives you what the final projection matrix is. And yeah, I won't work through the math there, but the 10-second explanation what should convince you of this is a low rank matrix, and the singular value decomposition gives you the low rank approximation. If it actually is low rank, it gives you the actual low rank values. That's all I'll say for people that this made sense for. And this didn't necessarily make sense to me a year ago. I had to like brush up on my
And
math
low
in order to
rank
understand this.
means low rank is essentially the dimensionality of your embedding space is much shorter than the number of samples you have.
Yes, it means that these vectors live that even though that they are in 100,000 dimensional output space, they actually live on a small, low dimensional hyperplane in the outputs. Yeah, so there's some fun math here that you know I hadn't touched. So I ostensibly I have a math degree, but I haven't used all that much of it in the last, let's say, 10, 15 years, and so it's fun to occasionally go in and get to actually use some of that stuff.
And so a lot is known about, at least for GPT-2, like the tokenization scheme and things like that. Like, do you rely on any of that knowledge?
No, we don't, but they actually publish it too. The reason why is because you want to know how much you're going to pay on a per token basis. And so most providers give you a way to tokenize and compute what the cost would be of a given query. OpenAI actually just gives you the full tokenization directly. They have this library called TikToken that is open source, and they just give you the full tokenization of all their models. And so this is not usually where the secret sauce lives. But if it were to be, we have another paper that shows
But
how to
that doesn't
recover
say
this
that
too.
if it were secret, it wouldn't be harder for you to do
Correct.
what you're
Yeah,
doing.
that's yeah. That this is it's not. We use a couple of facts about the tokenization, but not a lot. But people would in general want to reveal this anyway.
I was going to ask about mixture of experts, which is kind of an emerging architecture for these large scale models. Um, do we know enough about those architectures to say whether this attack might or might not work?
Yeah, so it should work identically because we make no assumptions on the internal representations of how those are computed for the model, as long as the final output projection is a linear transformation. Everything else will behave the same. And you will, of course, need to make very different approaches once you try and start to scale this attack up to recover, let's say, the layer before. Because if that has some mixture of expertise kind of thing, that might behave very differently. But as far as ours goes, we don't make any assumptions about what happens inside the model.
You wrote about this. You have a paper. Someone can't go and like perform this attack because turns out there's a remediation that you shared with OpenAI and Google. Like, talk a little bit about the remediation approach.
Yeah, sure. Yes. So this I think is one of the big successes from this paper that I'm happy about. What do I mean by this? For a very long time in adversarial machine learning, we have been producing attack after attack after attack. And the way that you know if an attack is really actually powerful is if people who are not security people decide to change the way that they do things because of your attack. So let's look at other areas. The way that your processor works. Like Intel and AMD have put security features on your processor because of particular attacks that security researchers have discovered. When you're on the network, you're connecting over HTTPS because of attacks that security researchers have demonstrated are possible. All of the pieces of every computer that we use today are informed by attacks that have previously existed, and we have built them in because people who are not security researchers have decided this attack is sufficiently worrying that I will change the way I do my things to stop that attack. In adversarial machine learning, we didn't have this for a very long time. The way that GPT-4 works would be functionally identical if the entire field of adversarial machine learning dropped off the face of the earth. Like, nothing that we learned in adversarial machine learning impacted the way that we designed the biggest models today. Like, no one trained them to be adversarially robust.
What are you saying that is saying something about?
I'm saying that we were thinking about problems.
I guess I'm thinking about like the old put a sticker on a stop sign and it turns into a picture of a giraffe, and like
correct,
people AV makers in theory like thought about these kinds of problems and did something to
maybe, but I have seen no evidence that any car manufacturer actually has done this. Why? Suppose that I wanted to make a car to crash. The adversary of someone who has the idea that they want to like cause your car to crash to kill you has many other ways to do this than like put a sticker on a stop sign. They could put a trash bag over the stop sign. That's probably a lot more effective than trying to construct a transferable physical world adversarial patch.
So it's kind of a critique on the
field
more so.
Yes.
Yeah. Okay.
Yeah, it's not critiquing everyone else. I'm saying that like we as a field have not produced a compelling enough attack that other people have been willing to change the way that they do things because of the attacks that we have. And so the reason I was excited that we sort of OpenAI and Google changed their APIs. They broke functionality to make their APIs a little bit less functional because of this attack. And so it tells me that like I have convinced someone else who is not a security person to do something that makes some of their customers less happy with how their API works, because they have viewed the attack as sufficiently advanced that they want to make sure that this can't be done. And so I think like sort of at a high level, independent of what the actual methodology was to fix it, I really like seeing the fact that we could finally convince someone to make a breaking change to fix some security problem. So I think that was very nice. Okay. Now let me talk for a second about what they actually did, which is a relatively simple fix. What they do is they make it so that you can no longer, for the same query, actually read off the probability distribution over all possible output tokens.
Was it previously all literally all? I thought it was 5.
Yeah, so it was 5. But what we showed how it was possible to use another parameter called logit bias to bring different tokens into the top 5 at different times. So you would query on some random prefix and you would get the top 5. And then you would say, okay, what about those 5? I'm going to bias those tokens to be plus 100, bring those into the top 5. And then you get another 5. And then you bring another tokens into the top 5 and you repeat this and you do this many, many, many times.
So you just have to, iterate it, by n over 5 or whatever.
Yeah. N over 4 because of some details.
Windowing and overlaps and stuff like
that. Okay. With very fancy math, you can get n over 5 to work. Some of the theory people on the paper showed this. It turns out to be numerically unstable, and so we did n over 4. But yeah, okay. There are lots of fun details here, but we don't have to get into all of them. But yeah, so the way that they fixed it is to make it so that if you send a query that has both asking for top P to like learn what the probabilities are, and you ask for a logic bias, then you can't do both at the same time. Like you can, the way that the logic bias works now is it sort of works after it tells you what the probabilities are. So you can always learn the top few probabilities. They increased it from top 5 to I think now top 20, but you don't get to bias these with the logic bias. So that's how the defense basically works.
Meaning the top 20 is invariant to the logic bias parameter.
Correct.
And I think you worked also with Google. Did they take the same remediation approach?
Yeah, so Google actually just banished logic bias entirely. It was like, let's just be extra safe about this, and they may at some point put it back at some in some safer way. Um, but yeah, so there is an attack in our paper that works with logic bias only without probabilities. It does some binary search. So what you do is you say, well, what is the value of token 12? Well, I'll increase its bias to be plus 100. Now it's almost certainly the most likely output. And then, so now I'll go to 50. And then maybe it still is. And I'll go to 25. And maybe it's not at this point. So now I go to 37.5. And you sort of do binary search to recover. And this is a much less efficient version of the attack. But in principle, it still works. And so the API that was at the time on Palm 2 just removed entirely the logic bias, and they may return it. I mean, this is ultimately a question of like what is the cost of the attack and what is the value of the information that you learn. And the cost of the attack can just be, you can count it for the version that we implemented. It was like a couple hundred to a couple $1,000. If you were to do it with this logic bias binary search trick, it's now I think 5 or 50x more expensive or something on this order. And so it ends up being 10,000 or maybe $100,000 depending on exactly what you want. And there's some value dollar amount at which it is cheaper to just train your own projection layer, and it's up to the company to decide like what is that value for them and which defenses do you want to put in place.
The implication of that last statement you made is that the reason why someone would be doing this is because it's cheaper to steal a projection layer than to create their own. But is that really the reason why somebody would do this?
Sure, okay, there are other reasons too. You might, for example, just be interested in learning the size of the model, and training my own is not going to help you here. It might be better for some attack, in which case training my own might not be helpful. But like very rarely is it the case that what you want is the projection layer. You probably want to do something else. You want to make another attack more efficient. And so in this case, it may be better to spend your $10,000 training some other transfer prior model and spending more on queries. Like there's the thing that you care about, and this is sort of instrumental in that way, but it's not like the ultimate thing you care about. So the question is like, as an adversary, where would I want to spend my money? And you just need to make sure that any piece of it is not like the most vulnerable piece, right? Like in principle, anything is broken under enough of a dollar value. Like no one wins against the NSA. Like so, like it's just like how much money does someone willing to spend in order to get the given thing, and as long as you've put it above the threshold of what it's worth, then like it's not economically efficient for the adversary to try and steal it in this way.
As a security researcher, do you have a sense for whether like there exists GPT-X 0-day market kind of thing? Like,
Yeah, this is a good question. I don't know actually right now. I think, this is a thing that exists in classical security, right? Where people they find 0 days in some software and they'll then go and sell them to the highest bidder, or if they're a nice person, they'll go to the bug bounty program the company provides and get the company will pay them for having found some security bugs. I don't know if this is a case right now. It may be, and I just don't know about it. But I think what's probably more likely is that there's just not yet a huge amount of economic value in any of these particular attacks. There's some, but it's not quite there yet. And also, many of the attacks are relatively easy to discover. And so it's not the case that they would command very high of a value, because you could probably have found it for less money by just doing the work yourself. Like all these attacks that we're finding, we publish the papers on them, and so you in principle could pay someone a large amount of money, but once the paper's on archive, you could just go and read the paper and then implement it. And so for many of these things, it's not the case that I think there's a reason for this to exist yet. But I think this is mostly a function of the fact that the total amount of value being driven through language models is only a very, very, very small fraction of the amount of value being driven through like the entire internet. And so it just makes sense the value of what you might pay for an exploit corresponds to what you can actually get out of it. And you just can't get that much out of these language models now. But it's a possible future if it turns out that this language model thing really does scale to be like truly amazing. I think it's entirely reasonable that the value of an exploit would scale with the value of what you can sort of get out of it.
And then it's another question whether those 0 days would be like model stealing versus privacy targeting versus some other thing.
Yeah, exactly. Yeah. And that's a question of what is the thing the adversary actually wants to achieve at the end of the day.
Right.
And I think this is a very important question that's nice to try and figure out what it is that we actually want to do.
Interesting. And so where do you see this particular research direction headed?
We're going in a couple directions with this. One direction we're working on right now, we have some preliminary results, is how to achieve the same thing with fewer assumptions. So I mentioned that we were trying to do previously this with this logic bias and this learning the probabilities and these things. And there's a question like, what if you don't have that? Can you still try and implement the attack? And
in other words, can you do it post mitigation?
Exactly. Yes. Like, and this is the question you always ask. Like, you've removed one thing for me to do. Like, what else can I do?
Right.
There are other questions of, can I extend this to 2 layers? Can I take a different approach that lets me to learn the first and second layer of the model instead of the last and second to last layer? There's lots of these kinds of questions. And at the same time, we're also doing, some basic research on these stealing attacks that try and scale it up from, these tiny 40 neuron models to, let's see if we can do 400, 4,000 neurons, and like just trying to approach the problem from all directions at the same time. And, most of these things won't work, but eventually you'll find an idea of it has one thing that has some promise, and then you'll push the field forward a tiny bit more, and then you hope that other people can do the same kinds of things.
Are there kind of qualitative merits one way or another for the kind of bottoms up to back down approaches to these things in terms of what you might expect to learn about the models?
No, I just think that you try and approach the problem from as many different angles as you can, and you try and see what value you can get from each. And you don't want to spend all of your time thinking about just one approach, even if it's been fruitful in the past, because there might be some very easy thing you can do in a different way. And we're trying to spend a little bit of time. Maybe it turns out that the last layer is like where you stop, and like going the second to last layer is just not worthwhile. And but even still, like, then maybe it's easier going. So it turns out that the reason we were doing this for the previous work is recovering the last layer in some cases, if you do go forwards, can be kind of challenging. And so getting the last layer in itself is actually useful for the other attack that just went forwards, because you go forward up to the last layer and you get the last layer for free. That's a win even by itself. And this is the kind of thing we were hoping for.
I mentioned at the very beginning that you won a best paper for another paper. This is like a position paper on differentially private learning with large-scale public pre-training. We might not be able to give this one the full treatment, but
no, that's fine. It's a much simpler paper.
All right, let's go for it. What's this one about?
Yeah, so this one has no technical results. It is just making an argument. It is making exactly one argument. So the paper is trying to say something about privacy. So first I have to tell you what people do. So back to data stealing. This question of you train a model on some private data and you're worried about someone who can recover the data. There exists a defense that prevents against data stealing called differential privacy. It is not from the machine learning field. It predates most of deep learning, and it comes from some other areas of statistical analysis of data. And what it does, it guarantees that no individual example can influence the final trained model by very much. And so you can provably say, if your model is trained with differential privacy and you set the parameters right, then you cannot have memorized any individual person's data. And so the model cannot ever emit people's data to anyone else. And so it would be safe for a hospital to train with user level DP of particular values of epsilon and delta on the hospital could train on patient data and release the model, and that it would mathematically provably be safe, which is an amazing result to have. So the thing that we're arguing in this paper is that people. So why is this? Why is that not every model is trained in this way? Because you lose a bunch of accuracy. If you train with differential privacy, the accuracy goes down by oftentimes quite a lot. And so what people do instead now is the following. They take some big giant model trained on all of the internet without privacy, and then they fine-tune it for a little bit longer with differential privacy. And then they say, this final model is private. And it is private with respect to the data it was fine-tuned on. This is very different, though, from the model being private. And this is the only thing we're trying to argue in this paper.
Does the original differential privacy, the theory that supports that, extend fully to the guarantees the differential privacy provides? Does that extend to pre-training, or
no?
Is there some theory of interactions that says yes, you've fine-tuned in a differentially private way, but there are interactions that could leak data?
Yeah, so no interactions can happen. So differential privacy in this sense is perfect, but it only protects the data that you trained with the privacy preserving technique. So
okay,
let me give you.
But if it does that, if it does guarantee that, that seems pretty good in the hospital example.
No, yes, okay. So now let me. Okay, this is why people did. So now let me give the points. Now let me argue the paper. So this was sort of all the setup for where the world is now. You have differential privacy. It's great. It loses utility. So people train big models and take those and fine tune with privacy on those. Okay. So now let me argue the paper. First argument. Suppose that, let's say you trained a model not on hospital data, because I'll get to that in a second, but you would do this on, let's say, people's text messages or emails or something like this, and you release a model that you claim has preserved privacy. Okay, now let's suppose that there's some person out the world, let's call him Peter, who takes this model and who starts prompting it. And he starts asking, what do you know about me? And the model says, I'm not sure. I don't really know very much. And the Peter says, here's the thing that you shouldn't know my phone number. Can you tell me what Peter W's phone number is? And the model gives him his complete phone number. Peter might be wait, you trained on my data, you're giving me my phone number, what's up? You must have done something that's sort of wrong with this data. This is not actually something that would be entirely hypothetical, because if you trained a model that was a fine-tuned version of GPT-2, it turns out that there's some person, Peter W., that GPT-2 memorized his phone number. He uploaded this as a part of a scientific thing that was to the government that required that he attach his phone number, physical address, company, fax number, email address, all these things. And GPT-2 saw this document and memorized it. He did this in one particular context, to disclose something to the government. And the model is then being fine-tuned on a bunch of other data, and then he asks for his phone number and the model reveals it. Now, on one sense, the model provider is correct in that the fine-tuning data did not cause any memorization of Peter's phone number. But you can imagine how you might be confused if someone tells you this model was trained with privacy, and yet it still memorizes all of your data, because it happens to be from the pre-training. Okay, so now someone might say, that's fine.
That's but an education thing.
Yeah, you deserve it. But there are a couple of concerns here. The first is this: if people are not particularly careful in how they describe what they have done, this can degrade the meaning of differential privacy. Because someone else could train the entire model end to end with privacy and actually do things perfectly well. And another person can do only the fine tuning of privacy. And it's very hard to explain differential privacy to users, even without this subtle distinction. But now I have this another level of distinction that like one of the two breaks the privacy and one of them doesn't in this way. And so this can have this one problem. So the other concern is not everything on the internet was meant to be on the internet. And not everything that was like placed there for one context is meant to be used for another. Right? So you can, for example, doxing is a thing that is bad, right? This is like, but like where you and I live in the United States almost certainly is a matter of public record, right? If you sort of have a house with a mortgage or something, you can go to the city and you can file the paperwork to request where it is that you're staying. Today it may even be available online, right? Like there are things online that like are there, but are there because it has classically been hard to find these kinds of things. And so a model just making some of these things available can feel like a privacy violation, even if technically the information was already still available. On the other hand, you also have things that were never intended to be put on the internet, but were put up there for a short period of time. A model was trained on them. They were then taken down, and now the only knowledge of this is contained in the model. So, for example, GPT-2 was trained on some uploads of people's conversations that were on IRC that were made available for a short period of time online through 4chan, then taken down. To the best of my knowledge, the only way to access these transcripts now is by querying GPT-2. So someone like had some private data, they uploaded, they took it down, and now it's only there. And so if you had a fine-tuned model of GPT-2, you would be revealing still this kind of data that is no longer available anywhere else. And so it is very much the case that not all data that is public is necessarily intentionally public. And so you have this world where people might be saying that things are privacy preserving because they want to make sure that they can get their utility back, but you end up sacrificing some other kind of privacy because you're preserving the mathematical definition, but privacy is one of the fields that how the user feels about their privacy matters like almost as much about as whether or not you're actually mathematically giving us a particular kind of thing. Because in many cases, the harm is not a real, like, in many cases, I don't lose monetary value for like some of these things that are private to me. Like, it's private to me. I would like it to be kept sensitive. And like, I can't necessarily put a dollar value on that. But so if a person feels like they have lost their privacy, in some sense, it is similar to as they actually have. Now, like this is the challenge of this field is you can't make this entirely a technical problem. And so we're not going to try and make the social arguments in our paper. We're just going to try and say there are lots of people who know how to make those kinds of arguments, and we need to be careful when we're using these words because we're talking about a mathematical definition, but it actually relates to real people, and we should acknowledge that people exist in the world.
And so to kind of restate that, it sounds like what you're saying is that applying the marketing terminology, differential privacy, to this partially differentially private pre-training scenario is confusing and potentially degrades the perceived value of differential privacy itself.
Yeah, and we make a couple other smaller arguments in the paper that talk about. So you asked about the hospital example. It turns out that it may be the case that you don't actually get better at doing hospital classification if you take one of these big pre-trained models because the benchmarks people use for private learning are the same as the benchmarks people use for standard learning. And we already know that models like are just zero shot good at all the benchmarks.
Right.
And so like to what extent, like there's a period of like 2 or 3 years.
So you're doing this bad thing that you probably don't even need to do anyway. It's
Exactly,
not helping
yes, right.
you solve your problem.
Yeah, like there's a period of 2 or 3 years with a state-of-the-art private technique was to take whatever the latest advanced best language model was and repeat the paper with a better language model. And like you get like a new state of the art in privacy, and you have done no privacy improvement. And so like you should be careful. Like, this is the other problem. It's like we should, have these like benchmarks that actually measure private learning, not measure accuracy on tasks that can just be zero shot solved by big giant foundation models.
And now the probably one of the most I don't know if popular is the right word, but one of the applications of like federated, learning potentially involving differential privacy is some of the new Apple Intelligence stuff that was released. Have you looked at what they are saying about what they're doing and how it applies to the considerations you're describing here?
Yeah, I haven't yet. I think this is like once it gets into the weeds of like how does the implementations actually match user expectations. I think this is one of the areas where people who study humans should really start to take a look at these kinds of things. Um, we wanted to write this paper. So the paper was mainly driven by Florian, one of the people who actually wrote the previous paper with me, and Gautam, who's another professor. And the reason we wanted to write this paper is we were sort of mostly attacking some of our own work in this paper. Like we sort of felt like we can make this argument because we had worked on some things that did this kind of thing, and so we could reasonably convince people like, look, we have done this too. We understand that this is a problem, and so you should like, we're not like attacking you for doing the bad thing. And so that's why we wanted to write this paper initially, but we do very much think that this is the kind of problem that should be studied by people who actually have the ability to like ask users what you feel about this thing. Like we're not
I mean, you're
necessarily
saying
the right.
people might confuse these things, but people could actually go out and figure out if people do confuse these things,
Yeah,
and that's not
exactly.
what you've done. Yeah.
No, exactly. Yeah, like you could ask people, maybe it turns out that you ask people, do you mind if a model learned on something that you put online, even if it wasn't intentional? Do you care about this? And they say no. And then fine, great, like we get to do it. Like, but like you have to be careful about how you set up that experiment. Like I am not someone who feels qualified to study people because I know that the way that which you phrase questions matters quite a lot. And someone could almost certainly answer this question much better than we can. And we just wanted to say, technically this distinction exists and a person may care. And so we should be careful in how we use these words.
Well, Nicholas, thanks so much for taking some time to catch up and
Sure.
get us up to date on what you're up to and how you're thinking about the field.
Yeah, of course. It's been great to talk to you.
It's been a pleasure. Thanks so much.
Thank you.